Black holes are perhaps the most mysterious objects in the universe. They are the consequence of gravity crushing a dying star without limit, leading to the formation of a true singularity, which perhaps happens when an entire star gets compressed down to a single point, yielding an object with infinite density. It's one of the most cherished science fiction scenarios, and is using a black hole as a portal to another dimension, time, or universe. This fantasy may be closer to reality than previously imagined. Rotating black holes serving as gentle portals for hyperspace travel. Professor of Physics, University of Massachusetts at Dartmouth, this is by Gaurav Khanna on Conversation. Black holes, perhaps the most mysterious objects in the universe. Consequence of gravity crushing a dying star. This dense and hot singularity punches a hole in the fabric of space-time itself, opening opportunity for hyperspace travel. That is, a shortcut through space-time, allowing for travel over cosmic-scale distances in a very short period of time. Researchers previously thought that any spacecraft attempting to use a black hole as a portal of this type would have to reckon with nature at its worst. The hot and dense singularity would cause a spacecraft, of course, to endure a sequence of increasingly uncomfortable tidal stretching and squeezing before being completely, of course, vaporized. Flying through a black hole? My team at the University of Massachusetts Dartmouth and a colleague at Georgia Gwinnett College have shown that all black holes are not created equal. If the black hole, like Sagittarius A, located at the center of our own galaxy, is large and rotating, then the outlook for the spacecraft changes dramatically. That's because the singularity that a spacecraft would have to contend with is very gentle and could allow for a very peaceful passage. The reason that this is possible is that the relevant singularity inside a rotating black hole is technically weak and thus does not damage objects that interact with it. At first, this fact may seem counterintuitive, but one can think of it as analogous to the common experience of quickly passing one's finger through a candle near 2,000-degree flame without getting burned. My colleague Lior Burko and I have been investigating the physics of black holes for over 2 decades. In 2016, my PhD student Carolyn Mallory, inspired by Christopher Nolan's blockbuster film Interstellar, set out to test if Cooper, that is Matthew McConaughey's character, could survive his fall deep into Gargantua, a fictional supermassive rapidly rotating black hole some 100 million times the mass of our sun. Interstellar was based on a book written by Nobel Prize-winning astrophysicist Kip Thorne, and Gargantua's physical properties are central to the plot of this Hollywood movie. Building on work done by physicist Amos Ory 2 decades prior, and armed with her strong computational skills, Mallory built a computer model that would capture most of the essential physics after the effects on the spacecraft or any large object falling into a large rotating black hole like Sagittarius A. Not even a bumpy ride? What she discovered is that under all conditions, an object falling into a rotating black hole would not experience infinitely large effects upon passage through the hole's so-called inner horizon singularity. This is a singularity that an object entering a black hole, a rotating black hole, cannot maneuver around or avoid. Not only that, under the right circumstances, these effects may be negligibly small, allowing for a rather comfortable passage through the singularity. In fact, there may be no noticeable effects on the falling object at all. This increases the feasibility of using large rotating black holes as portals for hyperspace travel. Mallory also discovered a feature that was not fully appreciated before: the fact that the effects of the singularity in the context of a rotating black hole would result in rapidly increasing cycles of stretching and squeezing on the spacecraft. But for very large black holes like Gargantua, the strength of this effect would be very small, so the spacecraft and any individuals on board would not detect it. The crucial point is that these effects do not increase without bound. In fact, they stay infinite, even though the stresses on the spacecraft tend to grow indefinitely as it approaches the black hole. There are a few important simplifying assumptions and resulting caveats in the context of Mallory's model. The main assumption is that the black hole under consideration is completely isolated and thus not subject to constant disturbances by a source such as another star in its vicinity or even any falling radiation. While this assumption allows important simplification, it's worth noting that most black holes are surrounded by cosmic material, dust, gas, and radiation. Therefore, a natural extension of Mallory's work would be to perform a similar study in the context of a more realistic astrophysical black hole. Mallory's approach of using a computer simulation to examine the effects of a black hole on an object is very common in the field of black hole physics. Needless to say, we do not have the capability of performing real experiments in or near black holes yet, so scientists resort to theory and simulations to develop an understanding by making predictions and new discoveries. If you'd like to join me on my Patreon account, you will hear content not covered by mainstream media. These riveting stories will be based on my research, and I will state my opinions and give my personal insight on diverse and controversial subjects and world events not covered by mainstream media, and not supported by YouTube guidelines. So whatever I have on my Patreon, most of those will not be on my YouTube channel. Please consider becoming a member today. More of the most significant and important videos will be on my Patreon channel. Your support helps me to continue my research and keeps this YouTube channel alive. And we depend on your support, your generous charity, because we help economically challenged families here in Athens, Greece, in Kapota, and we also help the young generation with university tuition and the community around our church. Thank you.